All right, today we're going to break down the incredible story of how modern artificial intelligence actually came to be. We're going to strip away all the hype, all the complicated jargon, and trace this whole revolution back to one surprisingly simple idea from way back in the 1940s.
I mean, it's pretty much the biggest question in technology right now, isn't it? We've got chatbots, self-driving cars. It really feels like we're surrounded by these thinking machines. But how? How did we get here? How do you actually teach a bunch of circuits to recognize, say, a picture of a cat, or to write a poem?
Well, the thing is, the answer isn't some single eureka moment. Nope. It's more like a 70-year journey. A journey of one core idea being built on, hitting dead ends, getting forgotten, and then being rediscovered. It's a story of false starts and absolutely incredible breakthroughs, and that is the journey we're going to go on right now.
Okay, so where does this whole 70-year saga even begin? We have to go all the way back. Way back to 1943. This is before silicon chips, before modern computers were even a thing. Two researchers, McCulloch and Pitts, they asked this brilliant question. Could we model a single brain cell using just simple math?
And this was their answer, the McCulloch-Pitts neuron. You could think of it as kind of the Adam and Eve of all AI. Now, the key thing to get here is that this neuron couldn't learn anything. It was just a simple little decision maker. Honestly, the best analogy is a light switch. It gets a few inputs, and if enough of them are on, bam, it flips its own switch to on. That's it.
The logic here is incredibly simple, really. It just counts up the number of incoming on signals, the ones. And if that number hits a target that you, the programmer, set, that's the threshold, it fires an on signal of its own. If it doesn't hit the target, it just stays off. The most important part? That threshold was fixed. It was hard-coded. It could never, ever change on its own.
And you know what? This simple little model was surprisingly powerful. For example, if you set that threshold to 2, the neuron perfectly mimics a logical AND gate, which is one of the basic building blocks of all computers. It only fires if input 1 and input 2 are both on. But, and this is the huge catch, it couldn't learn. If its logic was wrong for whatever task you gave it, well, it was just going to stay wrong forever. So, okay, that first neuron could do some math, but it couldn't learn. And that limitation, that was the next great challenge. The big breakthrough came in 1958, when a researcher named Frank Rosenblatt introduced a model that could do something, well, revolutionary. It could learn from data. He called it the perceptron. The perceptron was a major evolution. Instead of just adding up inputs, it assigned a weight, kind of like an importance score, to each one. And here's the magic trick. If the perceptron got an answer wrong, it would use this error correction rule to just tweak those weights a little bit, making it more likely to get it right the next time. For the first time, we had a machine that could learn from its mistakes.
And this table here, it really just lays out the massive leap we're talking about. The field went from a static, dumb calculator to a primitive learning machine. One model could only compute what you told it to. The new one could actually learn. This was an absolutely monumental shift in thinking.
But all that excitement, it hit a wall, a huge one. It was proven that a single perceptron was fundamentally unable to solve a surprisingly simple logic problem called XOR. Now think of it this way. The perceptron could only draw one single straight line to separate two groups of things. For a lot of problems, that's fine. But for the XOR problem, you just can't do it with one line. It's impossible. And this limitation, it was so profound that it cast this huge shadow over the entire field, leading to what we now call the first AI winter, a long period where funding and interest just completely dried up.
So, how did the field break through this wall? If one neuron, one single straight line, wasn't enough, what was the answer? Well, it turned out the solution wasn't a better neuron. The answer was just more of them, stacked together in a really clever new way.
And this is the multi-layer perceptron, or MLP. So instead of one neuron making one decision, you now have layers of them. The input data flows into the first layer, which passes its results to a hidden middle layer, which then passes its results to the final output layer. And by stacking them like this, suddenly the network could learn way more complex, nonlinear patterns, the exact kind that had totally stumped the single perceptron.
And here's just how powerful this idea of layering really is. There's this famous mathematical proof, and what it basically says is that a network with just one of these hidden layers is, in theory,
capable of approximating almost any continuous function you can possibly imagine. The potential here was suddenly immense.
Okay, but how do you train all of these interconnected neurons at the same time? The key is an algorithm called gradient descent. The best way to think about it is this. Imagine you're a hiker, you're blindfolded, you're on the side of a huge mountain, and your goal is to get to the lowest point in the valley. So at every step, what do? You'd feel the ground around you to find the steepest downward path, and you'd take one step in that direction. That is exactly what gradient descent does. It calculates the slope of the network's error and then nudges all the weights in the right direction to reduce that error, step by step.
So it sounds like they had it all figured out, right? I mean, by the 1980s, all the core ideas were there. But history repeated itself. Progress stalled out. The community had the blueprints for these incredibly powerful learning machines, but they were mostly just theoretical. To actually train them, you needed massive amounts of data and huge amounts of computing power. And back then, neither of those things existed. And so the field entered its second long, cold AI winter.
And that brings us to the modern era. Those ideas from the 80s, they were just lying dormant, waiting for the rest of the world to catch up. And then, in the early 2000s, the two missing ingredients finally showed up, creating what you could only call a perfect storm.
So first, you had powerful GPUs, graphics cards, originally built for video games. Well, it turns out they were perfect for the kind of math these networks needed. Second, the internet created a literal fire hose of data, images, text, video, all the fuel these models had been starving for. You combine that with some smarter, more efficient training methods, and the stage was set for an explosion.
And the flashpoint, the moment that everything changed for good, was the year 2012. A deep neural network called AlexNet entered a major computer vision competition, and it didn't just win, it completely demolished the competition. Its performance was so far beyond anything anyone had ever seen that it just shocked the entire research community. This was it. This was the definitive proof that deep, layered networks powered by GPUs and big data were the future. The deep learning boom had officially begun.
So just think about that incredible journey for a second. It all started with a simple on-off switch back in 1943. That tiny spark grew into a single neuron that could learn. That one neuron became the building block for powerful layered networks with this immense theoretical power. And finally, after decades of just waiting, the world of hardware and data caught up and unleashed everything we see all around us today.
You know, it's such a powerful reminder that the technologies that feel like they appear overnight are often built on decades of research, full of stops and starts and frustrations. And it really makes you wonder, right? What quiet foundational ideas are being worked on in labs right now that might take another few decades to truly blossom and reshape our world all over again?